everyone for for me the first colloquium talk of the year. So welcome to a new season, CMSA Colloquium. And today we're happy to have Clark Barwick from the University of Edinburgh. Clark is an expert on homotopy theory, higher category theory, and related subjects. Is that right? That's what I'm told. And
how about expert?
Before University of Edinburgh, he spent a few years here in Cambridge, right? MIT and in the math department field. So I figure that many people in the crowd know Clark. So thank you very much, and thank you for me.
Thanks so much. Thank you to the CMSA for the invitation to be here. I don't get to do this stuff as often as I used to, and I really I didn't appreciate it then, but I really appreciate it now. So I really thank you. I was told that this was going to be quite a general audience, so I don't want to get too far into the weeds. But I also want you to feel free to interrupt me as questions arise, or for us to. I hope this will be the start of conversations as well with lots of people. And so the program that's happening here right now is a program on arithmetic homotopy theory, or sorry, arithmetic quantum field theory.
Лена, сейчас лекция, я хочу послушать. Алло.
What is it? Oh, I see. So in arithmetic quantum field theory, what you're supposed to imagine is the following scenario. We're going to look at, well, I'm going to think about spec of the integers. There are ways to generalize this, but I'm just going to focus on this example just to sort of have something concrete to say. And the idea is that this thing is supposed to roughly be. Are we still good? I'm ringing, but that's okay. This is supposed to be roughly a 3-manifold. That's the story. Well, it's supposed to be an open 3-manifold. Maybe I'll emphasize that. It's got a point missing. That point missing corresponds to the Archimedean place. The Archimedean place, when we add that in, we get well, something, and that something is supposed to be thought of as now a closed 3-manifold. And this is just what you get by adding the Archimedean place to this. So the picture here is perhaps a little different from the one that, well, it's certainly different from the one that I learned in my first algebraic geometry class. You know, the picture that I learned of spec Z when I was taking algebraic geometry for the first time was something like the following. You have a nice generic point here, right? And then you have, maybe I'll color these since I have colors. And then you have the various closed points kind of sitting around that. So there's 3 and I don't know how many primes you want me to see, or you want me to write down, but I'll just write down that many. And sort of the picture is this roughly and this is a picture. What is this a picture of? This is a picture of spec Z with its Zariski topology. And one of the things that happens in algebraic geometry is that you don't always use the same set of lenses to look at your objects, right? So algebraic geometry provides you with a whole class of different lenses with respect to which you can look at your objects. So here I'm looking at this with just the Zariski lenses. I could have looked at this with some more refined kinds of lenses. I could look at this, for example, with the Étale topology lenses. And when I look at the Étale topology lenses, you start to see more of this 3-manifold type behavior. So you start to see something that lives over this, which looks like a 3-manifold. And well, how does it live over this? Well, I've got this sort of big bulk, which just lies over this generic point here. And then over each of these closed points, well, I have the Étale homotopy type of the residue field. So you don't have to know what that means, but you already know what the Étale homotopy type of spec of FP is. You know that it's BZ hat, right? It's the classifying space of Z hat. So it's generated by a single element, at least topologically speaking. So we think of this thing as a knot embedded in this 3 manifold. And I can't draw knots, so I'm just going to draw an unknot, but I twisted it up so it looks good. Right, and so these are the things that lie over these points here. So you get this kind of stratified space picture. And then the complement, what does the complement look like of all these knots simultaneously? So this is a picture. I'll draw this. This is a picture of spec of FP sitting inside here. And you've got a bunch of these. You've got one of these for every prime, and then you've got sort of whatever's left over, the bulk. And the bulk, what does that look like? That looks like spec of Q. And well, you know, if I'm thinking with étale eyes, this is, you know, S1, maybe profinitely completed. And this is the classifying space of the absolute Galois group of the rationals. Right, so you can think of the points of this knot here as various algebraic closures of spec FP, if you like. There's only one algebraic closure of spec FP up to isomorphism, but the space of those isomorphisms gives you this sort of non-trivial loop. Right, and this is the story of what's called arithmetic topology. Which, if you attended any of the sort of inaugural conference, you heard a lot more about this in much more detail than I'm going to provide here. But there, if you've never seen this before, there's sort of cute things that you get to be able to do now, right? So you get to do things like, well, if you've got 2 of these knots, then you can ask about their linking number. You have to do that modulo something, so you can look at the linking number, say modulo 2. Looking at their linking number modulo 2 turns out to be exactly computing the quadratic residue. And the fact that this knot is wrapped around this knot, the same number of times that this knot is wrapped around this knot, is precisely quadratic reciprocity. So there's little cute things that you get to do like that. So you can start to look for things like Baromean primes. It's a fun thing to do. So if you're ever 1361 and 937 is a set of Baromean primes. Never seen this before. That's a fun thing to do. Actually, that's the only one I know by heart. I mean, I think there's an infinite number of these, but I only know one example. And so this is the story of arithmetic topology. And the point of view with which I came into this was I was interested in actually understanding the topology of this thing. Yeah. In what sense is the absolute Galois group 3-dimensional? That's a great question. So let's have a look at it. So the first thing I need to tell you is that I do have to compactify to see the story that I want to tell you now. So I'm going to have to include that Archimedean place. The reason for that is that if I look at the étale homotopy type, well, this isn't the reason, but this is a reason. If I look at the étale homotopy type of spec Z, this is just contractible. It's not got anything interesting happening. So I have to add a point. So I'm going to do that. I'm going to add a point to this thing. And so when I add a point to this thing, this is the thing that I want you to think of as a three manifold. So why is this thing a 3 manifold? Well, it's because it's got a 3-dimensional Poincare duality. So you can write this thing down. The easiest way that I know to write this thing down is to just write it down kind of in a hackneyed way as a topos. And when you write this thing in a hackneyed way down as a topos, it's really quite a hackish construction that I have in mind. But when you do that, you see that you have a 3-dimensional duality statement. It's a weird kind of Poincare duality because if you think of the projection down to a point, then what you end up saying is something like the following. You end up saying that if you take P upper shriek of the constant sheaf at the dualizing object, so the dualizing object in this world is something like Q mod Z, then you get GM shifted by 3. So that 3 is the 3. That's the 3 right there of the 3-dimensionality. But you also get this GM here, which you might not be very happy about. That doesn't look like, that's just reflecting the fact that this is highly non-orientable. Right, and so in this world, you don't just have like finite orientation covers, you have these sort of enormous, complicated orientation covers. You don't need to. You don't need to say it with the Archimedean place in the Archimedean place present, but it's more annoying to do that to do without it. This is a cleaner perspective, I think, as it turns out. Yeah. And so, well, okay, so this is why this whole thing is three-dimensional. These things are just circles. There's nothing going on at all homotopically. There's no interesting things happening. And then you can do things like look at, you can thicken these circles up. Thickening these circles up means adding in more p torsion. And so you can take a limit of those things and you'll end up with ZP. And then, well, so that's like a tubular neighborhood around this knot. So the story goes. And then when you have this tubular neighborhood around this knot, well, what can you do? You can take just the boundary of that tubular neighborhood. And so that gives you something that looks like a knotted torus in here. And that knotted torus is supposed to correspond to QP in some sense. So I'm not very good at drawing this kind of thing, but I'm really not good at drawing this kind of thing. So I'm not going to try very hard. Yeah, okay, whatever. And so this green thing here, that's supposed to be spec of QP, at least morally. That's what you're supposed to have in mind. And then if you think about this, well, if you believe in this analogy, then you start to say, well, okay, how am I ever going to study these objects, right? I've got a three manifold, I've got some embedded knots, I have some deleted tubular neighborhoods of those knots, I've got stuff that I want to compute. And how do we ever compute these things? How do we ever study these things? Well, the best way is to try and think about some sort of physical theories, right? Like in three manifold theory, like if you really want to learn how three manifolds work, you want to sort of try and describe some physical theories on those three manifolds and study those. And so the idea is, well, I just want to do the same thing here with these things, these new bizarre objects. There's going to be some problems with this. There's a number of problems. One of the problems is that this non-orientability that I was alluding to. So here's one shadow of that non-orientability. I said that this thing without the bar is contractible. So, but you could ask, what do I get if I look at the Étale homotopy type of spec Z after completion? And well, it depends on how you set things up a little bit, but the way that I want to think about this is that it's homotopy equivalent to the suspension of RP2. So you already start to see that's a three manifold kind of, but it's the homotopy type of a three manifold morally, but it's very non-orientable, right? I mean, this is not going to be an orientable thing. That's okay. Well, I don't know. It's cohomological dimension 3. I don't know. I'm not going to push it much further than that because I'm not going to be able to, right? And sort of we're dancing around the fact that there's this sort of non-trivial problem here, which is that these things really aren't manifolds, right? There's just no way to see these things as manifolds. That's not going to happen. So what you might have hoped for, and I guess at one very early point when I first heard this story, what I did hope for was that you could just take this picture and then there was going to be some functor that said, turn your arithmetic scheme into like a manifold and like do the geometry on that manifold. And that actually will recover all the information that I want. By the way, let me just pause for a second here and point out something very critical here, which is I mentioned that this thing is three-dimensional and that it had this Poincare duality statement. I wrote this kind of thing down. GM shifted by 3. This kind of statement, what is this? How do you prove something like this? This is global duality, right? This is class field theory. This is global class field theory, right? And all of these assertions are class field theory. Like, so there's a statement that says that spec of QP has a two-dimensional duality, that's local duality, right? Well, dimension 1, it's so easy that it doesn't have a name, but it's also a statement about a form of class field theory. And so I'm going to come back to that point. So I'm just put a pin in that for now. Okay, so this is the world in which I'd like to live. And well, it's also the world that people like David Ben-Zvi want to live in and people like Min-Young Kim want to live in. And but I want to live in it in a slightly different way from the way in which they want to live in it, I think. So you can have two attitudes toward this story. One attitude that you can take toward this story is that this is a cute bedtime story. Thank you very much. I'll bear this in mind as I do my real mathematics. You know, and sort of get inspired by this sort of picture, but don't talk about it in public. Another point of view that you can take to these things is that, well, no, I want this geometry. I actually want to have these objects and I want to seriously treat these things. And I want to be able to think about honest field theories on these things. I actually want to get these geometric objects in hand well enough to be able to talk about field theories on them. And so that's the kind of thing that I'd like to talk about. So in some sense, the sort of upshot of this talk is going to be a little piece of formalism. And I'm just trying right now to explain why I'm so interested in that piece of formalism. And it's just, in some sense, it's just the beginning of a story. So I hope that, we have time to go further with it. Okay, so this is the dream. And now the dream doesn't stop here, right? The dream doesn't stop here at all because, well, once you have an idea for how arithmetic quantum field theory should work, then you want to sort of prove things like the Langlands conjectures, right? Which you can then restate as an equivalence of an equivalence between two four-dimensional field theories, as David has discussed. So, like, how are you ever going to say that, right? How are you ever going to talk about those things concretely? You can sort of tell the story of things that you extract from them, but if I wanted to work with actual field theories, how might I go about doing that? And so I want to go back to thinking about what this geometry is really doing here and how to really think about these things as geometric objects where I could do something like that. And well, the inspiration that I want to take comes from a piece of the local story. So the local story in this parlance is about spec of QP. And now if you think about spec of QP as spec of QP is a Zariski topological space, it's not very exciting. It's got a point and that's the end of the story. If you think about it at all cohomologically, well, that's fine. You end up with something. It's the sort of classifying space of the absolute Galois group of QP. That's a nice thing to contemplate. But this still has the disadvantage that this is just a homotopy type, right? So if I wanted to do some sort of field theory on this, I need more than just a homotopy type. So, I mean, just as a sidebar, remember that if you're talking about something like a topological field theory where your space-time is like Rn, well, you'll get a different answer if I choose a different n, right? There's you have different kinds of field theories. It depends on this. It doesn't depend just on the homotopy type of this manifold that you stick in, right? How could it possibly? So this isn't going to be enough to define a field theory. It's not sufficient structure. And so the question that I was interested in was I was interested in trying to understand what additional structure on these homotopy types could you possibly provide that would be sufficient to start producing field theories. So the idea is that we're working in this rather exotic world of strange geometric objects. And this rather exotic world of strange geometric objects, they don't have good notions of local points. Like, it's not the case that you can look at like a little disk-like neighborhood around every point of these things, right? We don't have that kind of language for these things. Nevertheless, it sort of seems sensible to sort of talk about field theories on these things. And the question is, how are you ever going to do that? And so I'm going to take my inspiration from back here when I think about topological field theories. And like, what do you need in order to give me a quantum field theory? Well, you need to be able to sort of say, all right, let me draw a sort of vague picture here. If I'm hanging out over here and I perform some observations, maybe in a little region of where I am over here, and I perform some observations of my quantum field theory, and you're over here and you make some observations some distance away, then we can combine those observations. That's a safe thing to do. Now, if you move too close to me, then our observations will interfere with each other and I won't be able to combine the observations. This is the essential idea behind what are called factorization algebras, which is in the title of my talk. And so the idea is that only once points are sufficiently far away can you combine observations that you make near those points. So I'm just going to take that sentence and parse it. So it's only when points are sufficiently far away, when they're apart, that you can talk about combining them. In other words, what I need in order to be able to talk about a field theory of some sort, in this case, a quantum field theory, is I need to be able to talk about 2 points being apart from one another. And I need to know what that means. So maybe I'll write this as the upshot. So to define factorization algebras, so the sort of system of observables corresponding to a quantum field theory, you need an additional structure, or at least you need some sort of structure. So you need some way to say that different points are different. Yeah.
Feel free to tell me this is like not a good question, but you were saying before, like, I need some extra structure to define a field theory. You said that, I want to define a field theory. If you're talking about defining factorization,
Yeah.
I would say normally, like, you have a field theory, it's defined by some actual, defined by like giving a manifold like a structure, it's defined by some fields, some whatever, and then you can try and compute things in that field theory. And
Yeah. Yeah.
So can I ask, are you sort of trying to tell us what I need to define a field theory, or what I need to compute things within a field?
That's a fair question. I don't know. I mean, I'm trying to tell you how to define a field theory, but on an exotic space-time, on a space-time. Well, actually, at the moment, it's just going to be a factorization algebra. It's not going to be more than that. So, which I agree is probably not the right thing to say. I was being very, very sloppy there. But yeah, no, for me right now, what it means is a factorization algebra, right? So a system of observables that do things in the right way. Is there a? You think it's a pretty good definition? I'm not going to get into I don't have anything to say about that, but I really mean just by that, I'm just being sloppy and saying factorization algebra. Like if I give you the system of observables, I'm declaring that enough for now and running away with it. But the key point that I want to make is that I want my spacetimes to be weird. I want to allow all kinds of freaky stuff in my spacetimes. What do I mean by freaky stuff in my spacetimes? Well, there's an enhancement of this thing here. Right? This is just a raw homotopy type, and we were a little unhappy about that. We can improve that homotopy type. This can be enhanced to what's called the Farg-Fontaine curve. This was defined by Farg and Fontaine. And the idea of this Farg-Fontaine curve is that well, I can give you a precise definition, but instead what I want to say is that you want to think of this thing as sort of giving you the honest two-dimensional object here that was in green, this knotted torus that we were trying to write down. Not really a torus, it's non-orientable, but and this thing has different points. In fact, the points of this thing, like if you're looking at the R points, how does this thing exist? Let's think about how this thing exists. This thing exists. The way I like to think of it is that I think of this thing as an assignment that carries perfectoid rings and characteristic P. And it spits out a set. And what do you do? Well, what you do is you take a perfectoid ring and characteristic P and you extract what are called the untilts. So if you don't know what that means, don't worry. I'm not going to use it in a non-trivial way. I'm emphasizing here the fact that this is a very, very exotic sort of geometric object, right? I haven't written down something that looks like a manifold at all. Nevertheless, it is sensible to treat it as a manifold. And I want to try and figure out how factorization algebras can be defined on it. And so this thing exists as part of a kind of a Grothendiekian perspective on what geometry really is. So what Grothendieck said about what a geometric object is that, well, it's a topological space. X along with a sheaf of functions on it, so a sheaf of commutative rings, O of X. This is the usual way of setting up geometry in Grothendieck's perspective. And that's true, but as I mentioned before, it's not all that there is to the story, right? It's not just that we have this topological space in this sheaf of rings. We also have another thing that we can do, which is we can look at, I mean, this sheaf of rings, this will give rise, if you like, to the theory of quasi-coherent modules over OX. And that's one way to sort of study the geometry of this thing. So for example, X groups in this category give coherent cohomology of your scheme, right? But that's just one of many categories that you could try to attach to this thing. There's all sorts of other categories that you could attach to this thing, like for example, the category of constructible sheaves on X, valued in something, I don't care. Right, and this gives you another answer for what the geometry should be telling you. And this gives you a very different answer from the way this geometry works. This geometry is different from this in a very serious way. And there are other examples, right? There's sort of other more exotic examples. There's sort of, well, so if I'm in characteristic 0, then I can look at something like the category of D modules, for example. And I can look at crystalline things. And there's a whole bevy of these things. And in each case, well, the kind of cohomology that you want to compute is computed by looking at X groups in these various categories. So another way to say what geometry is, sort of following Grothendieck. Grothendieck says that it's a topological space along with a sheaf of rings. I can talk about a geometric context as some sort of collection, some sort of category of geometric objects, along with a sheaf of symmetric monoidal categories. For experts, these are not categories, but infinity categories, and I'm usually working with something like PRL. It's the right thing to say here. So, okay, so the situation is the following. We have some geometric objects. Those geometric objects come to us as, well, some category of gadgets, and then the lens with which I choose to look at those gadgets, right, which is given to you by this sheaf of symmetric monoidal categories, and then X groups in those categories will compute the cohomology relative to that theory. So now I'm interested in sort of a categorification of Grothendieck's picture, where I have this as my sort of starting data. This is the geometric context in which I choose to work. So when I say it like that, when I say it in this incredibly general way, well, then I can allow all kinds of interesting things. So for example, it doesn't have to come from algebraic geometry. So for example, I can have X be the category of homotopy types, or animae, if you're into that sort of language. And then this A here, what can this A do? Well, it can take an anima X, and you can look at locally constant sheaves on that anima. So locally constant sheaves on that anima means that you're looking at functors from X into, well, whatever spectra. And this is in some infinity categorical sense. So this is the correct notion of locally constant sheaves valued in something derived. And this needs the whole homotopy type to recover it. So this is some sort of monodromy type statement. But there are also these other examples here where I take the category of schemes and I can look at quasi-coherent sheaves, or I can look at constructible sheaves or whatever. I have some sheaf theory that's attached to this thing, and that's part of this story. Okay, so given those data, given that all that data, can I extract from this story the notion of a factorization algebra? So if I have just an object of this category X, whatever it is, like a scheme, in this case, just a homotopy type, can I extract a factorization algebra? And we've already seen the answer is no. But the question is, what else do I need? And the claim is that the extra piece of information that I need is the information of what it means for 2 points here to be distinct. That sounds like it couldn't possibly be enough information, but I claim that it is. So here's the statement. I'm going to enhance X to a slightly bigger category, well, actually a much bigger category. And that much bigger category is going to consist of objects of X along with the notion of what it means for 2 points to be different. And this is what I call a world object. So I've got a proper piece of chalk here. So a world object. And I'm not, by the way, the papers about this aren't out yet. So if you think a name that I'm giving is really bad, please tell me and I'll change it. So a world object. Yeah, exactly. So the idea is that this is something that could be a viable space-time. That's the idea. So a world object is it's going to be a functor from a certain category that I'll tell you about to, well, this geometric category. So this category D, what is this category D? This category D is going to be the category of finite sets and inequivalence relations. This is a little bit of perversity that I like to introduce. So this is finite sets and inequivalence relations. So what that means is that it's the complement of an equivalence relation. So I'm saying it's a finite set, and I tell you what it means for 2 points to not be equivalent, right? Well, that's the same thing as an equivalence relation, except that here the maps that I'm thinking about, the maps preserve inequivalence, or equivalently, they reflect equivalence. Right? So the objects here all look like things like 1 plus 2, right? So this is a set with 3 elements, and it's got 2 equivalence classes, one with 1 element, one with 2 elements. And I've got a map in this category D. This is a map in D from 3 to 1 plus 2. So you have these maps that I call dispersive maps, where you say, okay, I had 3 elements, and now I want this one to be different from these other 2. That's the kind of thing that you have. I'm not done with this definition. I have to say stuff. I'll say what that stuff is in a minute here. So, but how do I want you to think about this? I want you to think about this in the following way. I want you to think that if you give me sort of x1 plus 2, then this is your space of triples x, y, z, such that, well, x is different from y, and also x is different from z. There's something kind of funny about this, right? One of the funny things about this is that this is going to have, I've got this map here from 3 to 1 plus 2. This map here has this object here has a map down to x cubed. And so what do I have? Well, if I have a triple of points here, whatever I mean by point, I'm being vague about that, but morally, what do I have up here? Well, I have the space of ways for x to be separated from both y and z, to be pulled apart from both y and z. And the point is that that's a non-trivial space. That's an interesting space. It's probably not just a yes or no question about whether X is different from Y and Z. It's probably a space of ways for X to be moved away from Y and Z. That's the fiber of this thing. Yeah, it's the space of ways for X to be different from both. This isn't great notation, but. So if you like homotopy theory, this might be sort of familiar to you, right? I mean, this is sort of like, let me lower the number here just so I can. There. Let me lower the number here just so I can kind of make things a little simpler here. So this is the space of ways for X to be different from Y. Right, and the claim is that that's a non-trivial piece of structure. It's just a configuration space, right? This is just X cross X minus the diagonal morally. But the point that I want to make is that I'm adding this in as additional structure on top of X. So even if I don't already have an X that comes to me as like a manifold where I know what it means for 2 points to be different, I can give this thing an extra artificial notion of what it means for 2 points to be different, satisfying some stuff. I'll have to tell you about that stuff. And as long as I do that, then I can define one of these world objects. So for example, let's think about a situation where I don't really have a great notion of point. Let's think about the example of, I'll erase this and write it again.
Tell us about an example where you do have a good notion of point. Like if X is R2.
Yeah.
I'm imagining that the bottom one is copies of R2 and the top one is just configuration space.
Exactly. Yeah, precisely right. Yeah. So you can look at, so if X is equal to R2, then you know, X1 plus 1 is just what you said. It's the set of pairs X comma Y in X2 such that X is like not Y. Right? It's really that stupid.
So here, the fibers are all contractible.
The fibers are all contractible because in a manifold, there's only one way for 2 points to be different. They just have to be different, right? But if I now change this and I work with the homotopy type of R2 instead, if I work with the homotopy type of R2, well, I don't know. The way I write homotopy type is I write pi infinity. Then I'm looking at the homotopy type of this thing. Right, the homotopy type of R2 is contractible. This is the least interesting thing ever. This is relatively interesting anyway. It's a circle. This is the homotopy type of this set here. And now when I write down a map down to pi x2, well, this is again contractible. It's not very exciting. But the fibers, well, the fibers, there's only one point here, right? And so the fiber here is the space of ways for X to be different from itself. And that's an S1. And more generally, if I made it an Rn, then I'd have an n-1 sphere for this kind of thing. So this space here, how should we be thinking of this thing? More generally, these kinds of spaces, how should we be thinking of this thing? Well, I think the way that I'm currently thinking about it, and I'm prepared to be a little moved on this because this is a little bit new, but the way that I want to think about this is that I want to think about this as the space of ways of moving X and Y apart in such a way that it doesn't affect any of the observations that could be made on any quantum field theory for this object. That's morally the thing I'm trying to parameterize here. So as you point out, if I've got a manifold, if these things are actually manifolds, if I'm looking at world manifolds, then they're these fibers are boring, right? And that's for good reason. You can't expect to do that. You can't expect to move things off. However, from this homotopical perspective, here I'm going to try and pick up topological field theories or locally constant factorization algebras. And there I do expect to be able to move points off of one another and not change any of the observations that I've made in my system. So, okay, now I have to tell you a little bit more. So these are the basic objects. These are world objects. And if you've got if you've got some geometric objects that you like, you can start to pass to the category of world objects. You do have to have some conditions on these diagrams. I'm not going to just allow arbitrary diagrams. But the kinds of conditions that you want are, they're kind of reasonable. So here's an example of the kind of condition that you want. I'm maybe not going to tell you unless you press me. I'm not going to tell you what the condition is in general, but let me just do a special case here. So suppose that I look at this product. Right, so this is the space of pairs x comma z, where x and z are different, right? And this is just some extra y that I'm just throwing into the story. Now, if I just throw in this y, then the thing that you know about it is that it has to be different from either x or z, right? Because x and z are different. So it has to be different from one of them. So what does this say? This says that this thing is a push out. What push out is it? It's the union of these two under x1 plus 1 plus 1. And this is representative of the kind of formula that you have to have, you know, for there's higher versions of all this. And the formulas are a little weird in this story, right? I mean, these are strange conditions. This is saying that some limit of the values of this functor equals some colimit of the values of this functor. This is a really weird category. It's not, it's strange. And I don't know how to keep it from being this strange. It seems to have to be this strange at some level. Okay, so this is the kind of condition that you have to satisfy in order to be a world object. I do not want the functor to be monoidal. No. No, I don't want the functor to be monoidal. But you are right, however, that D here, I didn't emphasize this enough, this category D does have a symmetric monoidal structure, namely plus. That's not the coproduct or the product, it's just some symmetric monoidal structure. So, you know, does everybody know what I mean when I write this? Yeah, it's just a disjoint union and you know, like if I have like whatever, if I have two of these sort of partitions, then you know, everything here is different from everything here. Right, and that is a symmetric monoidal structure on this thing, but it's not the coproduct, and it won't be preserved by this x here. That's not going to happen. But I will come back to that because it will be relevant. Okay, so what's the circumstance? Let's go back. So the circumstance is, like, this is really formalism, right? When I said it was formalism, I meant it. It's just pure formalism. I've got a category of geometric objects that I like, and I have a way of computing their cohomology that I like. I want to think of this A as a way of computing the cohomology of these geometric objects. Properly speaking, it's a sheaf of symmetric monoidal categories. Whatever. And these data together are going to be what I want in order to start to define field theories once I have a world object of X. So now, if X, and sorry, I just made the mistake that you don't want me to make. I said field theory when I really meant factorization algebra. But so suppose that I have a world object in X, and I have this data over here, then I claim that I can write down a category of factorization algebras on X with coefficients in A. Okay, so let's do that. Is everybody happy? That says PRL, and I probably should have just written cat to keep compatible with what I wrote before, but secretly it's PRL. Like presentable categories, if you know what that is. And if you don't, think of cat. At the level of specificity I'm working at here, cat's good enough for our purposes. Although eventually it won't be, but let's not come to it. So, okay, all right. So what now are factorization algebras? So I've got this world object, and I've got my sheaf theory, and I want to put these together to give you a notion of factorization algebra. Okay. You look like you have a question.
Okay. You said you give a non-trivial example for object.
Did you not feel like that the pi infinity of the reals was, or pi infinity of R2, did you not feel like that was? So I mean, more generally, right, if I've got a manifold, actually, let me answer the question. I can do better. I can do better. So, okay, so if I've got that's a fair point. So if I've got a manifold, then I'll just use the distinction of points as you know it and love it, right? So that's fine. What if I had like a scheme, let's say a scheme over the complex numbers here. Maybe it's just a variety over the complex numbers. Well, I mean, what I really want to say here is I want to say the complement of the diagonal inside here, right? Notice that, like, I never know how to say this. Like, if you look at the t points of this thing, the thing that it isn't is it's not x of t cross x of t minus the diagonal, because that doesn't have good local to global properties. So I have to do a local to global thing, right? So this really is, like, if I put the complex numbers here, this really is, that's the right formula. But if I replace that with some other ring, that's probably not the right formula anymore, because I need those points that don't, that factor through the complement of the diagonal. Because being equal is a local condition, but being unequal is not a local condition. Okay, so that's the kind of subtlety that you can capture this, but I can do better. So one of the things that always bothered me about the usual approach to factorization algebras, like through Ron spaces and that sort of thing, was the fact that I could never see how these things were ever going to be functorial, right? If I've got a smooth map between manifolds, I don't have an induced map on the Ron spaces. Unless it's injection, but that's not the inspiring example that I want to think about. I want to think about things like projection down to a point. Something like that. So how could I possibly deal with that? Well, what I do is when I think about the world objects attached to these things, well, it's not like I have a map from here to here, but what I have instead is a span. And how does that span look? Well, this is the, you say that 2 points here are different if and only if they become different down here. Right, so that's a non-trivial example, and it recovers some functoriality that you might not have had before if you're willing to pass to spans. Yeah. Taking the image. Well, it would be a map, but it wouldn't be a stratified map. And ultimately, you'll want a stratified map. Yeah.
What are the that's not this?
Yeah, I mean, there's different ways to say it. I mean, yeah, so you could say that 2 points are locally distinct. Yeah, all right. So there are pairs of points in, yeah, I'll do this, okay. So these are pairs of t points, but the condition on them isn't that they need to be distinct, but that they need to be locally distinct. So these are pairs of t points such that for every geometric point, if you look at, oh God, terrible notation. So sorry. Geometric point will be called phi now. Then xc is not equal to yc. That's the correct thing to say. Well, it doesn't matter. I'll just pull it back. If I don't hit something in t, that's okay. Not my fault. I need this to be the same on all points of the topos, if you like. Yeah, so you make it, you're basically making it local, but that's the right thing to do, right? That's exactly the same thing as saying that t here has to factor through the complement of the diagonal. If you're buying that. Okay, so this is an extremely general setup. I've got a world object which is some sort of geometric object, but a family of geometric objects connected by all these different maps. And I've got a sheaf theory attached to this, and I want to define a category of factorization algebras. And maybe now I should emphasize that the definition that I'm about to give, I mean, this basically already exists in the literature. I mean, I learned the definition that I'm about to give basically from Sam Raskin. So I better write his name here, who will be here later at some point. But so here's the definition. So the definition is that if you have a world object X and you have this A here, well, what can you do? Well, A, remember, is a sheaf of symmetric monoidal categories. Cat, I'm saying cat here. And well, what can I do with this thing? Well, one way of saying what I'm going to do is I'm going to take a lax limit. So that is to say, I'm going to have X, which is going to give me a functor from D to X op. I'm just opping the usual functor. And then I have A here, which goes to C alg. And I'm going to take a lax limit of these things. So there are different ways to sort of say that. One way to say that that's quite handy is that you can sort of reorganize this information as a functor from some category down to D, such that the fibers of this functor are exactly the values of this functor. Too many copies of the word functor in that sentence, but it really does make sense the way I said it. So the values of this functor are exactly the fibers of this functor. This is the unstraightening construction, if you like. And this is actually a symmetric monoidal functor because of this condition here. And so what I'm going to require is that I have a symmetric monoidal section. And so that's what it is. That's what a factorization algebra is. It's a symmetric monoidal section of this thing. So a factorization algebra of this thing is like a, I don't have great notation for this. I'm happy for any suggestions about how I can make my notation better. Symmetric monoidal sections of this thing. Right. So let's unpack that. Let's see that that really agrees with something that we recognize, and then I guess I'll actually be done. So let's see that this is something that we really recognize. So let's think about what the data of one of these things has to provide. Well, what it has to provide is that for every lambda, for every single partition in D, we have to write down a sheaf. And where does that sheaf live? It's one of our fancy sheaves, whatever kinds of sheaves we're talking about, on X to the lambda. And well, and this has to be compatible with morphisms in the way that's more or less obvious. But the symmetric monoidality, that's the interesting bit, because what does that say? That says that if you look here at this object, where does this live? This lives in A of X lambda plus mu. That's right. This is the set. This is where the lambda points and the mu points are distinct, right? And this has to be the same as the tensor product. This is like an external tensor product of F lambda with F mu. A priori, this external product, where does it live? It lives in X lambda cross X mu. But I have this natural map from X lambda plus mu to X lambda cross X mu. And so I'm going to restrict this to there. So I don't know, maybe I'll call this J or something. And this is J upper star of that. So these are what factorization algebras are. These factorization algebras, I claim that this is the natural notion of commutative ring in this context. This is what a sheaf of commutative rings is in this world. So what that means is that when you pass from X to world objects of X, the functions on objects of X become observables in quantum field theories on the world objects. That's how the functions work in this new context. All right, so this is the setup. This is the basic idea. And the idea is now that what we're going to do is we're going to make some judicious choices of our x's, right? What kinds of x's are we going to want to talk about? Well, the place to begin is probably with this example of the Farg-Fontaine curve. So, or I don't know if that's the place to begin. It's a place to begin. It's the place where I began. Yeah. Ah, right. Thank you. Thank you very much. Yeah, sorry, I should do that first. Yeah, thank you. All right, so let's look at, sorry, thank you very much. So let's look at the situation. So I'm going to answer this question, but I'm going to first answer the question that you didn't ask, which is, well, what if I do this one where I took x to be n and I took a to be locally constant sheaves? Then this reproduces locally constant factorization algebras, as you know and love them. Just does. What's that? With any world object. If you have a world anima, then you can talk about locally constant factorization algebras on that world anima. If you happen to, if that world object happens to have been pi infinity of your favorite manifold, then it will cover the definition that you already know about. Now, if I wanted not locally constant factorization algebras, but something a little more sophisticated, if I wanted some subtler kind of notion, well, what could I do? Well, one option would be I could look at, I'm just going to write manifold here. Technically speaking, you probably need something a little bigger than this for the whole theory to work well, but this is good enough for the purposes that I'm giving here. And if I took A to be, well, here I'm going to have to do something like look at co-sheaves for the Weiss topology on M. Well, this is what A of M is. If you don't know what this is, that's okay. This is just the topology that arises in the Castello-Guilliam approach to factorization algebras. And then, so yeah, these are Castello-Guilliam style factorization algebras that you get out of this story. And then, well, what else can I do? Well, I can look at x to be varieties over the complex numbers. And then, well, what can I do for A here? Well, maybe for A of my favorite variety of the complex numbers, I'm going to take some category of D modules on X. Right. And this recovers, well, there's some details here, but this recovers the Valens and Drinfeld story. So this is sort of one way of producing all of these different kinds of examples all in one kind of package. And then I guess the third example, and I'm almost out of time here, but the third example that I really want to press us into thinking about, and I don't have anything to say about it, so it's good that I'm stopping now. But I think we should be thinking about the theory of analytic stacks. So the analytic stacks, this is in the form, and this is as described by Clausen and Schulze. And it turns out, and I don't really have time to get into this, but it turns out that QCO is really going to be the right thing to do here. It turns out, all good sheaf theories turn into quasi-coherent modules on an appropriate analytic stack. There's some yoga about this that's out there. So I think that this is going to be a really exciting example, and in particular, the Farg-Fontaine curve is going to live here. I don't have any theorems for you yet about the Farg-Fontaine curve. The only theorem I do have, this is literally the unique theorem of the talk, I guess, but the only theorem I do have, which I can share, is that if this is part of a six-functor formalism, so if it has the full sort of apparatus of geometry and Grothendieck sense, then it extends to a six-functor formalism here on world objects. And that gives you a lot of the functorialities that you know and love in the usual theories of factorization algebras. Okay, but now I definitely have to stop. Thanks so much. I appreciate it.
In your example 1 and 2, I guess I understand the world and how to think about world objects.
Yeah, I don't think there is a way to make every object into a world object. That's right. That's right. Yeah. So another way of thinking about this is that you're taking, if you've got a manifold M, you can enrich the homotopy type of that manifold to a world anima instead of just an anima. Oh, I don't have anything to report except that I think I wanted to propose that as an avenue of discussion for all of us. Well, yeah, I can construct an example of, I can construct two examples of factorization algebras on the Farg-Fontaine curve, which should agree under Langland's duality, at least up to mistakes. But these questions about how to choose exactly the right category and stuff like that, and I might make a mistake there if I tried to do it here. But yeah, I mean, so you can construct examples there. They all come from the same kind of thing. You do something like look at the affine-Grassmannian on the Farg-Fontaine curve. By the way, the affine-Grassmannian is another interesting example. Like if you're working, I don't know, if you're working here and you've got yourself a reductive group, then you can look at the affine-Grassmannian relative to that reductive group, and that will have the structure of a factorization stack on your curve, say. That's just a thing that you can do. Yeah.
The last theorem you stated.
Yeah, I didn't state it well. That's why. Yeah. Yeah. No, you're right. You're right. It's true. What's the correct statement isn't that factorization algebras extend the six-functor formalism. The statement is that if I cover up this symmetric monoidal structure here, then that has the six-functor formalism, and then. Yeah, exactly. And you're looking at algebras in there and watching for compatibilities and things. That's what I should have said. I just didn't say it right. Thanks.
But maybe to follow up on the Farg-Fontaine question, if can I expect that factorization algebra in your sense on the anima, which is not the case of the Colloquium, agree with a suitable class of local constant factorization algebras in the Farg-Fontaine curve?
Yeah.
That's a thing that I already know.
Absolutely. Yeah. Those two are the same. Yeah. That's a theorem. I'm comfortable calling that one a theorem. That's true. That's a true sentence to say. Wow. Yeah. Yeah. It does. Where do you want it to go?
Oh, if I just looking at something.
Oh, well, so you see, the problem is that my input here is homotopy types. It's not anything where I don't know what other kind of factorization algebras I might even hope for on a homotopy type. Right? Because I don't like the only sheaf theory I know how to build is locally constant sheaves on a homotopy type. I don't know how to do better than that. And so the idea is just that if I enhance that homotopy type, like that's already a general statement, right? That's some sort of monodromy sentence, right? So, locally constant sheaves are representations of pi1, or if you want to do locally constant sheaves of homotopical things, then you need the whole homotopy type of X. And the question is, if you want to have factorization algebras, how do you have to enrich that homotopy type? And the answer is, well, you do this world thing, and that does the job. But I don't know how to do something more sophisticated than that or I don't know how to get a more sophisticated kind of factorization algebra out of something that's just a homotopy type. Do I? I don't think I do. I don't feel like I do. Maybe you do. Yeah. Yeah.
And I kind of hope to turn the crank here and start outputting some kind of factorization algebra observable to that theory.
What a fantastic question. It's so good I can't even answer. No, yeah, I think that's exactly the right question. I just don't know how to answer it. I think that's a great question. Yeah. I don't know, but I hope so. Yeah. Oh, yeah, yeah. So there's a question of, yeah, it's like, this is a really, I don't have a really great theory for how that whole picture would operate, like how you pass between different geometric contexts. Do you want motivic factorization algebras? Is that what you're trying?
Just more like,
Yeah, I mean, I was, yeah, well, I don't know. I think this is more or less the words as people use them, right? It's just, but you're just saying that there are better choices I could have made here. Yeah.
He has line one.
Yeah, locally constant, I mean, the point here is that I don't have any interesting geometry here to work with except for locally constant geometry in some sense. So, I mean, but maybe your point is that there's no other reasonable kind of sheaf theory on a. Oh, okay. Oh, I see. Okay. All right. Yeah. Maybe. Yeah, I think so. So let me say what I can say about that. And this is also not a complete story yet. And I want help completing it because I really don't know how to do this story right. But like yeah, sort of. I mean, so David and I were actually just talking about this. So that so suppose you've got a world object, right? Then I can produce a new world object. And the new world object, it's kind of like I don't know, it's some sort of weird suspension of this thing. I don't know how to think about this yet, but you sort of form this kind of push out. This is hard to think about. At least I find it hard to think about. So this is some sort of, yeah, there's the same on both sides. So I'm gluing together X and X cross X with itself, but then I'm taking out the diagonal. Like I'm gluing over the complement of the diagonal, right? So I'm kind of doubling up the points over this. So now suppose that you want to see a defect on some Z sitting inside here, right? Some closed Z sitting inside here. Well, then I reckon you'll just pull this thing back. I don't reckon. It's true that you just pull this thing back. And when you pull this thing back, you're getting exactly the space where you have X with Z doubled. Right. You're getting exactly X with Z doubled. And then, so in fact, if you want to produce the Hecke stack as a factorization stack, it's actually Weil restriction from this to X dot. That's actually basically how you build it. It's a Weil restriction from this gadget, this weird suspension thing. And that description, because this is a suspension, that description shows you that it's a factorization algebra, but it's a monoid object in factorization algebras. Because that's what happens when you map out of a suspension. And so that's the structure that you know and love from wherever you think about these things. But that's the structure that you want on the Hecke stack. Did I answer that question? Did I? Okay. So this is the kind of thing that you can do. This is a sort of fun. I don't know if this thing has a name already in the literature. I don't know. Just like. Well, it is. I mean, the fibers of this thing are ravioli, I guess. Yeah, this is the universal raviolo or something. I don't know. I'm not gonna try to.
No more questions. Before we can clap again, if you want to join our speaker dinner and you haven't told me yet, please let me know now. And we will leave at 6 on the main lobby. There was another question? Oh. No, okay, so.
Where are we going?
The answer to this question depends on the.
Ah, okay. All right. I see. Because if we go to Toscana, we can have ravioli.
Yeah.
And I really wanna, that feels important to me. I don't know.
Okay, let's stop here.
Thank you.